Let me explain you the experiment. What here you see is a simple pendulum which is made from a bicycle spoke, and then there is a bob here, and then on top we have put a small tire motor which is connected to these wires. So you know, in a motor, when we give voltage, it rotates. Here it is reverse. When it is oscillating, it will generate a voltage, and this voltage generated is going to be read by this data acquisition card. So this data acquisition card takes this voltage and feeds to the computer. So that's what we have the arrangement. So now you can see that this pendulum is stationary, and then on the screen we have a small LabVIEW program which is going to read the voltage given by this data acquisition card. So when I run the program, what you see is that it is just recording 0 volt, it is noise, and as soon as I give some displacement in the pendulum, you can see the corresponding oscillations are recorded in this small LabVIEW program. So that is our experimental arrangement for this demo experiment, and let us see what do we have. Okay, so we shall start the experiment. For this I give the displacement. Now it is oscillating. We will start our program here. Let us say we start from here. You can see that there is oscillation because of the friction. There is a damping, so maximum displacement is decreasing in each cycle. So that's what we see here. Now let us stop the data taking and try to analyze this amplitude according to this equation. So we know that the damped oscillation is given by this A exponential minus gamma t by 2 cos twice pi nu t plus alpha, where A is amplitude. So for this data you can see that amplitude should be approximately at 0.02. So let us try to put it. So you see that this red line is going to be the curve generated by this equation. Now we will try to fix this damping parameter gamma. Gamma, what we do is that let us just put some number 0.01. Then you see that this is showing that it is increasing. Now we will try to increase this number. Instead of 0.1, we will make it, let us say, 0.4. You can see this is approximately following the maximum displacement of each cycle. If I increase 0.45, it is still there. Now let us try to see the frequency. Suppose I take 0.01, what you see is that this is decreasing, so it has to be much faster than this. So instead of 0.01, let us make it 0.1. So it is still higher. I will make 0.5. You see that this is now coming up, and still what we see is that it is higher frequency. So it is going to be, let us say, 0.8 somewhere. Let us try for that. So that is still more, so 0.9. So at least for a couple of seconds you can see that there is a match, but it is still faster. I will make it 0.95 and let us see what happens. This is too fast, so it is between 0.95 and 0.9, so somewhere let us say 0.92 if you do. Now you can see that it is nicely matching with the theoretical generated curve, and it is amazing to see we have experimental data which we can write it mathematically.